All right, so it's great to welcome TOMAS GONDA to our seminar. So TOMAS did his PhD at Perimeter Institute with Rob Speckens, and he's visiting us now from Innsbruck and is talking about work that he's doing with, I see a lot of people, also including like Tobias Fritz and many others. Yeah, the stage is yours.
Thank you, Marcus, and thank you for hosting me here. It's always very nice to be in Vienna, and I also enjoyed Jan's talk and the discussion that goes on. It feels like a very nice place to be here and to like engaging. So yeah, this work is a kind of line of papers and projects that has been going on since 2019, or around that time, when Tobias Fritz somehow came up with this idea to use tools from category theory in order to kind of give like a new language and a new way to think of probability theory. And the idea, I guess, is to go beyond like how we think of probability theory in 20th century, which is in mathematical language using measure theory and kind of setting up measurable spaces. Maybe there's some topology, or we give just the measurable sets. And this is very analytical. It's kind of bottom up. We set up, we need to know like very much like about the details of like the systems and so on. And so this approach is kind of opposite. It's top-down approach where we don't necessarily need to know all the details of the structure of these spaces that we are working in, but rather we kind of use structural properties of information flow. And so in order to kind of get us somehow get some intuition for what we'll be doing, I will give an overview of the diagrams that we will be describing flow of information. So here is one example of why this might be useful or interesting. And so that's the idea of conditional independence, which is useful for example, in the context of causal modeling or testing causal hypotheses. So Reichenbach's principle, one of its consequences is that if we have a common cause between, can I use this? Yeah. Where some event C is a common cause of A and B, then we should expect there to be a conditional independence, so that A and B are actually independent events when we know C, because there is no direct causal link between them. And so in this way, observing conditional independence can be a way to test causal hypotheses about what is going on in the underlying kind of way that the data has been generated. So when we look at the standard, maybe probability theory language in just discrete probability theory, these are two of several actually ways in which we can define conditional independence in terms of probability. So one would be to say that the probability of A given BC is actually not dependent on B, but it's just given by the probability of A given C alone. Okay. This should not happen. Okay. Or we can also do it in terms of the joint probability of A and B given C that it factorizes. Now, this is, I guess, okay, but it is a kind of additional equation that we may need to check on our probability distributions. Maybe we have to compute the conditionals, and then we have to check whether this equation is satisfied. And in the diagrams, I guess the idea would be that the conditional independence can be read kind of from the structure of the diagram alone. So as a kind of teaser for later, the expression of this conditional independence would look something like this. It's also an equation between diagrams, but when we build these diagrams from smaller pieces into bigger pieces, then this conditional independence can be somehow baked in somehow automatically in the way that the diagrams are built. And so this is kind of a key way in which the diagrams kind of encode some information about the flow of information. Here's some motivations that, I guess for me, like one of the reasons to work on this topic is that there are also motivations coming from different directions. So one of the motivations that I express is that maybe we have some new language that's in some ways or for some situations more intuitive, and we can use these diagrams to visualize what is going on. Another motivation could be that actually these diagrams can be interpreted in different models of probability. And so then we can reason independent of whether we consider discrete spaces or continuous spaces or some particular type of measurable spaces or possibilistic uncertainty. There's a whole host of different models that where our reasoning will apply to. Then there is the idea that this is a kind of synthetic approach where we specify some structural properties of the language that it should satisfy, and then we can just use these as kind of ingredients in our proofs and we'll see how that goes. Like there are some axioms that we can impose, that are structural axioms, and these can be used in proofs of different results. One of the new motivations that's kind of emerging is that people who try to build probabilistic programming languages, which have kind of internal ways of conditioning and doing Bayesian updating and so on, are interested in this categorical language as a way of giving syntax, formal syntax to these programming languages. And another idea, which comes from maybe more the mathematical perspective, is that we could hope to give, I guess, new models that go beyond measure theory and generalize it in various ways that are interesting. And maybe an important point on that for this audience is that in this talk I will not be talking about generalization to quantum theory, also because the theory that I will present actually does not have a quantum model. And there are some people who try to kind of extend the theory or maybe adjust it so that quantum theory would be somehow part of the description, but that's not what I'll be talking about today. We can also talk later about that if you want. Okay, so let's move to description of the language. So one of the results that I will use as a kind of starting point towards the language is Bayes' theorem. And so Bayes' theorem, on the left-hand side, I will be drawing or like writing the expressions either in discrete probability language or maybe in measure-theoretic language, depending on which one you are familiar with, you can kind of look at. And then on the right-hand side, the corresponding expressions in the diagrams to kind of express the correspondence and where we can kind of get towards what these diagrams mean, how we can interpret them. So first of all, a state in a Markov category, which is denoted by like this, like a triangle with a wire going up, would just be a probability distribution or a probability measure in the measure theoretic context. That's a state. And I think I need to keep touching this so that it doesn't. Okay. Then we can have a notion of a joint state where it's not just a probability distribution on a single state space, but maybe we have two sample spaces, A and B, and a joint probability distribution, or indeed a joint probability measure. We can take marginals, so this black dot just refers to marginalizing, so summing over the outcomes or looking at the measure with the full B set. We can look at the idea of independence, or that there is actually no correlation present. So this would be independence without conditioning. And for states, that would be the fact that the joint state just factorizes into splits into two pieces, like independent state on A, independent state on B. So that's just a product distribution. Or on the other side, we can look at the notion of perfect correlation. So perfect correlation would mean that our joint state on sample spaces that are identical, in this case, looks like a probability distribution P of A that that is on the diagonal, right? So that was me, sorry. So it is only non-zero for the diagonal elements of the product space. That's what the delta says. Sorry? P of A, P of B, delta AB. Yes, yes, you're right. Yeah, indeed. There should not be P of B here. Yeah, thank you. So that's the perfect correlation. And now we go beyond just mere states where we have outputs, but we include inputs. So now we have a box with an input A and an output B. That would be a morphism in our categorical language. For the discrete probability case, that's just a stochastic matrix. It's a conditional probability of B given A, where we need to satisfy that for each input, the output is actually a normalized probability distribution. And in the continuous case, the somehow corresponding idea is the notion of a Markov kernel. So Markov kernel is similarly, we can think of it as a conditional probability measure, where given each input, we get a probability measure on the output. And this dependence should also be measurable in the input. And this, in a way, because in category theory, morphisms are somehow the basic structure, that one could say that the way in which this categorical probability language is set up is to place somehow primary importance or to morphisms like this, so stochastic matrices or Markov kernels, and everything else is kind of derived from the way in which these morphisms compose and interact together, or maybe decompose. Of course, there are some special morphisms. So in a category, we always have identities. And so the identity morphism, which is just a wire, would be the identity stochastic matrix, or indeed a Markov kernel that takes an input and produces the delta measure on that input. And then we have this morphism that we have already seen, a wire with a dot, and we call that discarding. It is a morphism of this type, so it goes from some sample space or some object A, and the output is an object I. So this is a special object that is actually a unit for parallel composition. And in our concrete example, so in I, this unit would be just a singleton set, so just like a single outcome. And then the discarding morphism is just the unique stochastic matrix with a single outcome on the output, and similarly for the Markov kernel. And you can indeed see that if you take a joint state and you compose it with a discarding morphism, then you get marginalization. Besides discarding, one of the key really somehow pieces of structure that does a lot of the work for, well, one thing for the diagrammatic language, but also then for the properties that we can use in Markov categories and the proofs that we can do is copying. So this is, of course, the reason why we cannot have quantum theory as a naive kind of model of the theory, because copying would not be a quantum channel. We describe it like this. So it's just a wire that splits into two wires. And so for the stochastic matrices, it would be a stochastic matrix that takes an input and produces identical outputs to the input, right? And similarly for the Markov kernel, the idea is the same. So it is really just a process that takes any input and produces 2 copies of it. Another piece of machinery that we need is how to compose morphisms. And one way to compose morphisms is to take 2 morphisms where one output and one input match, and then stick them together. So this is called a sequential composition. For stochastic maps or stochastic matrices, this would be just given by the law of total probability. So we sum over the intermediate sample space, and then we look at the conditional of the overall output given the input. And for Markov kernels, we have to integrate over the intermediate sample space. And the other type of composition that we will use is parallel composition, where we can have independent processes that happen in parallel. There we have unrestricted input and output, and for matrices, that's going to be just the product of the conditional probabilities for each of the processes, and similarly also for the Markov kernels. Okay, so these are somehow the basic building blocks of the diagrams. And now we can understand the diagrammatic basis theorem, okay? So when we look at the right-hand side now, so here we have a joint state on two outputs. And it has some kind of decomposition where we can look at the marginal on just one of the outputs. And then this marginal produces the second output. So if you look at the left-hand side, so we have a joint distribution that splits as a product of the marginal on A and the conditional probability distribution of B given A. So that's how we can think of the equation on the right-hand side as expressing somehow in our categorical language this basic fact of classical probability theory. And there is a corresponding version also for the measure-theoretic language, of course. Yeah. Yeah, so the answer is no. Basically, indeed, so that's a very good question. So in this left-hand side, we can, of course, divide by P of A as long as it's non-zero, and what we get is a formula for the conditional probability. And this is kind of going into the distinction between the two languages. So on the left, we have more information, and we can do some concrete computations, while on the right, we only express kind of part of the information, and in particular, it's kind of the dependent structure or the kind of, yeah, like conditional independence and stuff like that. And in order to maybe have like an explicit expression for, you know, what you would do to extract this morphism and maybe divide by, you know, the marginal, that's not an operation that we have available on the right. And so this seems like a somehow like shortcoming of the language on the right, and I guess you could also see it as a shortcoming. The surprising thing, at least for me, and I think for a lot of us working on these projects, is that you can do a lot with just that, without having to compute this, without having to divide, without, you know, doing stuff like that. And so, in some sense, it's an open question how far that goes, and we don't know, and we are trying to push and kind of express as much as possible, kind of in terms of these structural properties, and we don't know where is the boundary. Like, there will certainly be statements that you cannot express in this way unless and until you have like a complete axiomatization of probability theory, basically. Yeah. Yes, so that would be the statement of the theorem in the diagrammatic language is that for every joint state Q, there exists a morphism like this that witnesses this equation. Yeah, indeed. Yeah. And this is indeed, so this statement that such a morphism exists is not true in every model of a Markov category. There will be some where it is true and some where it is not true. And this distinction, in some sense, also points towards the models which are more like probability theory and models which are more unlike probability theory. Okay, so now kind of having seen the diagrams, I can give you a definition of a Markov category. So Markov category for us is a kind of categorical structure that allows us to formally talk about this language. And so it is a symmetric monoidal category. So that just means that we have these parallel and sequential compositions, and together with some isomorphisms that mean that the diagrams make sense and we can move things around without changing what the morphism is. So there are morphisms, there's sequential composition, parallel composition, and on top of that we have these two special morphisms. So we have the copying and the discarding for every object in the category. And they also have to satisfy some compatibility conditions. So we would expect that if we copy an input and then we discard one of the outputs, then that's the same as doing nothing. That's the unitality condition here. If we copy and then we swap the two copies, it's the same as just copying. So there's the commutativity. And then there's also associativity condition and some other compatibilities with the parallel composition. This on its own is already giving you quite a lot of structure about conditional independence. And then in a Markov category, additionally, we often also impose, or for Markov category, we impose that when we discard the output of a morphism is the same as discarding the input. So in probability theory for stochastic matrices, this would just impose that the output of a stochastic matrix is a normalized probability distribution. So this gives us the normalization condition of probability. But you could also consider somehow like relaxing of this condition where maybe normalization of probability is not the most important to you, and then you would drop this condition and a lot of the theory still goes through, maybe with slight modifications. Yeah. 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 Yeah, so there's just a wire. Yeah, so I is the unit of the monoidal product. And so it is an object that when I tensor it with anything else, it is isomorphic to the original object. And it is also the output of the discarding. So it plays kind of dual role in Markov category, actually. It's a unit of the tensor product and is also output of the discarding. Okay, so this is kind of as much category theory as there is for today, basically. Just the definition. And now, so I told you about somehow different models of the theory. And so in our experience, we have come up with certain models that we are interested in, but we by no means have like a characterization of what the general models look like. So here are some examples. We already have seen the category, Markov category Finstoch. So this is a category where we have finite sets as objects, and the stochastic matrices that are the morphisms. Then on the right-hand side here, that was the second example that we have seen. It's a category where objects are measurable spaces, suitably nice, so that we have properties that we want. I will get to that later. And then the morphisms are just Markov kernels between these measurable spaces. But then there are different, maybe more exotic, maybe less well-motivated, but also yeah, maybe also interesting examples. One is the category Gauss, where each object can be seen as a real vector space with finite dimension, let's say. And then the morphisms are kind of like conditional distributions where the output is Gaussian. So that's maybe interesting in a certain context where you want to impose the assumption of normal distributions and then reason kind of internally only about normal distributions. There is a kind of continuous version of Borel-Stock basically. So you can consider topological spaces and then Markov kernels, which additionally have to be continuous. Then Finetti multi at the bottom here, that's more like a possibilistic version where you don't consider probabilities between 0 and 1, but basically stochastic matrices which can only take values 0 or 1, where 1 would describe that the outcome is possible and 0 would be the impossible outcome. And then here I just put some other examples. It's not so important to go through all the details, but yeah, you can replace basically the stochastic matrices with here they would be valued in the unit interval, of course. Here they are valued in the two-element set, true or false. But you can also consider values in an arbitrary commutative semiring, and that still works. And that gives a lot of different examples with various properties. You can look at unital function between monoids. So this is actually, as long as they are commutative monoids, then something like commutative C-star algebras, this will give you a kind of algebraic perspective on probability theory. Of course, what we have seen like from Jan's talk is the extension to non-commutative spaces, and this will not work because the copying will not be a morphism. But if you restrict to commutative ones, then copying will be commutative. And then there are some other ones. I will not go into the details. But suffice to say, there are a lot of examples, but there are also some non-examples. So I didn't put it on the slide here, but one thing that I have been interested in recently is these models of imprecise probability, where you, instead of a single distribution, you consider a whole collection of distributions as possible expressions of uncertainty, and this will not be a model of Markov category. You would have to change the categorical structure a little bit to allow for that. And there are also other non-examples that we are interested in, and I guess part of the development of the whole theory is also maybe generalizing what I am telling you today to situations that go beyond that. Yeah, something like that. I think the idea usually is that this set of probability distributions describes uncertainty about the probability distribution. So yeah, indeed, yeah. Yeah, so basically what we don't have in that case, we will not have actually a symmetric monoidal category. So we will not be able to satisfy the axioms of the symmetric monoidal category, because if I have a like a morphism, maybe actually I can write here. So if I have a morphism like this and like this, like F and G, then in a symmetric monoidal category, I would expect that I can interchange them. So there's the interchange law, that this is actually equal or maybe isomorphic, but in these models, this is not true. So in measure theory, this would be called Fubini's theorem. So it's about the interchange of integration. And for imprecise probability, this interchange fails. Yeah. Yes. Yeah, I guess it's part of the symmetric part. I mean, no, this is actually the monoidal part. So this does not involve like swapping. Yeah. So it's not even, it's, I guess, what people call pre-monoidal category. So this is something that, yeah, one of the generalizations is to not consider monoidal categories, but ones where, yeah, you don't have this isomorphism, but maybe you can do it only up to some other modification. Okay, now somehow going back to the starting point and the idea of conditional independence, how does it look like in this language? We see that now that we focus on morphisms, like we have both outputs and inputs. And so that means we can also condition on outputs, condition on inputs, and we get somehow, at least a priori, different notions of conditional independence. So on the top left, this was the original thing that I told you about. Now we have a tripartite probability distribution that splits, decomposes in this way. We have some prior distribution on C, and then we can generate A and B conditional on C. Okay, and the diagrammatic representation is precisely this. Then we can have a situation where we actually have a morphism with some input and two outputs, and we want to express that the two outputs are independent conditional on the input. Well, that would be kind of like one of the definitions that I told you in discrete probability, where AB given C, the probability splits as a product. And a third version is that we have an output A and an input B that should be independent conditional on another input C. And so that's kind of like this third definition of a conditional independence. And so in classical probability theory, these three definitions are equivalent basically by Bayes' theorem. And it's very much the same story here. So if we do have a Markov category that somehow satisfies this categorical Bayes' theorem, then these definitions will be also equivalent. But there will be also Markov categories where this is not the case, and these are actually somehow just distinct notion of conditional independence. And one very nice thing, I guess, about the whole story regarding conditional independence is that when we work with conditional independence, there are these rules that we can use to take existing conditional independence relations and generate new ones. And it's an algorithmic procedure. There are these semi-graphoid axioms that you can use to generate all the conditional independence relations, and three of them actually follow very directly from the diagrammatic language. So just by the kind of topological nature of the diagrams, you get three of the semi-graphoid axioms, and that's, I think, quite nice. Like they are kind of baked into the diagrammatic language. And then there is the last one, which is the weak union semi-graphoid axiom. That one actually does not hold in every Markov category. And it turns out that you need this additional property that the Bayes theorem holds in order to derive it. So that's the like interesting part of the story, I guess. Okay, so I've been talking about I should not move this too much because I've been talking about the diagrammatic language, and I guess I want to give you a little bit of sense of what we have been trying to do with it. Because of course, maybe it's nice that you can draw the diagrams and kind of visualize what's happening and visualize how maybe an argument about probabilistic process looks like as a diagram, but is that really like everything? And then, of course, we can maybe try to generalize the standard theory, but then I also told you that there are these non-examples, and yeah, as has been pointed out, and also not all statements about the standard theory actually can be expressed in the language. So what is really what is the core of why we are doing it? I think one of the things that we have learned is that we can follow something like the following procedure. So we look at some feature of probability theory. And this could be something like the fact that we have conditional probability. So we can take a joint probability distribution and we can extract what is the conditional. So this is a feature of probability theory. And then we try to extract, maybe a key property is a bit too strong, but some structural feature of this fact. So what is the structural feature? Is the fact that we have this joint probability that splits into the marginal and the conditional. Okay, so this is the structural piece of this feature. Okay, and now we have this structural piece. Now we can use somehow work entirely in the categorical language and try to construct an abstract, sometimes even purely diagrammatic argument to use this feature, this axiom, to prove something at the level of Markov category. So this would be something like a definite theorem in the language of Markov categories. And now that we have that, we can then look at like in which Markov categories, in which models does this categorical result apply? Where does it instantiate? And then we obtain classical definite theorem, maybe for Borel measurable spaces, or actually also in some new context that we didn't have before. And so this is a lot of what our projects have been about, is somehow doing this for various kind of features, and in particular trying to obtain somehow categorical versions of theorems of classical probability that would then recover the kind of standard theory as a special case. That's kind of how we are approaching this work. Okay, so of course now the question is, what are these axioms and what are the results that we can prove? So in the remaining time, I will try to tell you a little bit about these axioms and what are the results that we have been able to show so far. Okay, so in the next part, I'll talk about somehow on top of the basic structure of a Markov category, what are the concepts that we can define, what are the axioms we can impose in order to construct these arguments. One we have seen already, it's conditionals. So this is the Bayes theorem as I have been drawing it. And we can also consider a kind of parametrized version of the Bayes theorem, where instead of the joint probability, we now have a morphism with two outputs. And then the conditional, and the conditional now also depends on the overall input of f. And so we would say that a Markov category has conditionals if for any morphism on the left, there is a morphism like this on the right that satisfies this equation. Okay. And we can then look at the various models and ask this question, does the Markov category have conditionals? Well, it turns out that the stochastic matrices, Finstoch does, Borel-Stoch does, Gaussian does, the possibilistic case does, and also these quasi-measurable spaces. But, for example, the continuous case doesn't, because conditionals are in general not continuous. This I did not describe, but this is the case of stochastic matrices with negative or positive probabilities. So this would be allowing negative probabilities. There are also no conditionals there. And in the commutative series algebra, we also don't have conditionals. So it already somehow tells us in the examples that we have, which of the examples behave more like somehow discrete classical probability and which examples are somehow different, of different kind. Another very important definition, and this plays a role in many of the arguments and many of the concepts, is the idea of determinism. So we can ask for a morphism to be basically commute with the copying, and this tells us in a lot of the concrete examples whether the morphism has some uncertainty or not. And so the idea is that if I take the copy of an output of a deterministic morphism, then I could just copy the input and apply the morphism twice. And then if we look at some more concrete examples of categories, then for stochastic maps, these turn out to be the functions, so 0, 1 valued stochastic maps. For the Markov kernels, these are just measurable maps, or the continuous maps in the continuous case. For the Gaussian case, they are affine transformations without additional noise. And in the algebraic case, they're the homomorphisms, the monoid homomorphisms. So in basically, there are some very exotic examples of Markov categories that I did not tell you about, but in all the kind of reasonable examples, this notion of determinism kind of does what we expect, basically. Another important concept which shows up, in my experience, it shows up in the categorical language more than I would have expected, is this idea of almost sure equality. A lot of the proofs that we construct use notions of almost sure equality in some way. And so this is an idea that we have two morphisms, F and G, and they are not equal as morphisms, but they are equal if we look at somehow its input on some measure, but then we also observe the input. So what does this mean more concretely? It means that they are indeed equal as stochastic maps, stochastic matrices, but only for those inputs which are in the support of the probability distribution. So only for those inputs where the probability of A is non-zero. So in other ways, we could say that the probability of the probability of the two stochastic maps being equal is 1. That's kind of what the almost sure equality is saying. They are equal up to measure 0. And it's a very similar story in Borel-Stock. So again, it can be interpreted as saying that the probability that two Markov kernels are equal is 1. If I look at the time, I will skip positivity. So this is another notion that you can express or kind of rule out negative probabilities, and it shows up in various arguments, but I will skip it for time. Here is an idea which just disappeared about having a notion of a space of distributions. So when we look at, in some Markov categories, we would like to have a kind of correspondence between states, so probability measures or distributions on A, and deterministic states on some other object, which would be elements of the space of distribution. Okay, and we can also generalize this not to just to states, but also for morphisms. So we would have a bijective correspondence between stochastic maps into A and just functions into the space of distributions. Okay, and indeed, it turns out that for a lot of the examples that we like and are somehow sufficiently infinite, this works. It does not work for Finstock because there the space of distributions is infinite and we only consider finite sets, and so it cannot work. But for the other examples, this can be made to work. And then we can talk about this distribution object and this deterministic version of a indeterministic map. One of the, I guess, one way to see it in Borel-Stock is that to each measure on a set, so let's say we have a set of 3 outcomes, 0, 1, 2, and the distribution, the measure is quarter, quarter, and 1/2. Well, then the corresponding deterministic is just the delta measure on this distribution inside the space of all distributions on 3 outcomes. Okay, that's kind of how we think of this correspondence. Or for thin-set multi-case, the possibilistic case. There we have multi-valued functions. So this is one multi-valued function. It takes 0 to both outcomes and 1 to 1. Well, then the corresponding deterministic function takes 1 to the set that only contains 1, and it takes 0 to the set that contains both 0 and 1. And so on the right, this is a function, it's deterministic. On the right is multi-valued, and so it's not deterministic. Once again, very similar idea. I will skip this. No, this is important. So because we have this bijective correspondence, we can look at, in particular, the identity as one of the deterministic maps on the right. And then we get on the left-hand side, we get a corresponding map, or in this case, yeah, a general morphism that goes from P of A to A. And we interpret this map as a sampling morphism. We call it the sampling morphism. And in Borel-Stock, for example, it takes a measure mu, and it evaluates it on the set from the output space. So in this sampling map, one way to think of it in the diagrams, when it appears, it takes a measure and it samples an outcome from that measure. Okay, one other idea before going to the theorems is the idea of infinite products. So a lot of the arguments in classical probability theory involve infinite sequences of outcomes. And in order to do that, we need a notion of infinite product, because in the categorical language, we only have finite products. And I don't want to go into the whole details, but basically the idea is that infinite tensor product is something like a compatible family of finite tensor products. And we can look at when that exists, and indeed, somehow, of course, the cases where we have finite sets as objects that will not work, but for the measurable, the measure-theoretic examples, indeed, we have infinite tensor product, at least for countable cardinalities. Yeah. You don't need to take a closure. There is some choice that you have to make, because basically we require a notion of categorical limit, and then that depends on the morphisms that you choose in your limit cones. And here we choose the deterministic ones, and if you chose non-deterministic, you would get a different notion of an infinite product. So there is some choice involved, but it's not directly related to any topology. Yeah. Right, and then one kind of morphism that we can construct is a kind of IID morphism that constructs a independent sequence of IID observations. So we have an input that we copy infinitely many times, and then we apply the same Markov kernel or sampling procedure in each case. Indeed, like for the sampling morphism, this is kind of very important in the definiteness theorem, for example. I will show you. One other feature of this infinite product is that whenever we have a permutation of the indexing set, so the natural numbers, for example, then this permutation corresponds to some morphism that just permutes the elements of the product. And similarly, I will actually not use this, but if you have an injective map, then you can also marginalize any of the inputs that don't feature in the output of this map, and in this way somehow reorganize the elements of the tensor product. Maybe just look at the sequence from the second element, as in this case. I will skip the Cauchy-Schwarz axiom. There are many other concepts. So we have been able to express supports, absolute continuity, and many others. I will not go through the list, but I can send you the slides if you want. There are also other axioms that we can impose. We have a notion of causality and other notions, but actually in our experience, or like our aim is not to just increase the list of axioms indefinitely, but rather have some set of basic axioms that appear in many arguments over and over, and kind of see these as the kind of key building blocks, structural building blocks. Okay, so in the remaining time, I will tell you a little bit, at least, what are the results that we have been able to establish with this setup. First is the separation criterion, which actually Andreas, who's sitting here, has worked on. And this is a criterion for telling, kind of identifying conditional independencies in Bayesian networks. And I have already told you that given a causal structure like this one or like this one, we can construct a corresponding string diagram that expresses somehow the fact that this causal structure is how the data is generated, or can be seen generated that way. And in this case, on the common cause, we have the conditional independence, and the way we see it in diagram is that if we go back, we delete the wire that we condition on and everything that's connected to it through copying, and then we ask, are the outputs A and B disconnected in this resulting diagram? And so in this way, there's like a diagrammatic way to see the conditional independence just purely from the diagram. It's very similar in this second case, so we delete the conditioned variable C, and we see A and B are now disconnected, and so we have conditional independence. Now in this last case, this is called the collider. We have C is generated from A and B, and so if we delete C, we cannot go through this morphism, and so A and B are still connected, and so we don't have conditional independence. While if we were to look at A and B, not conditionally independent, but just independent, then we would have independence, because when we marginalize the output of the morphism, that's the same as marginalizing the inputs. And when we marginalize the inputs, then we just get a product distribution, and we have the independence. So this is how diagrammatically we can see that conditioning on additional variable can create correlation. And the separation criterion is a kind of systematic way to do this. And Andreas and Tobias have shown that if you have A and B outcomes separated by another outcome, or even a whole set of outcomes, then you have the conditional independence for any string diagram that witnesses that, that causal structure. Another result that has been quite important for us is the Finetti theorem. So for Finetti theorem, we'll look at a certain class of measures over sequences, which are not necessarily IID, but are exchangeable. So if we permute the outcomes, then the morphism is unchanged. So this is permutation invariance or exchangeability. And the Finetti theorem then says, okay, under some assumptions, so these are kind of the axioms that I told you about, we have that any exchangeable morphism then splits into this form where we have some morphism into the space of distribution. So this is kind of the Finetti measure, which is then sampled independently. And so in this way, we can view any exchangeable measure as a measure over IID measures. And actually, we have now two versions of the Finetti theorem with two different assumptions. And maybe one point that I wanted to highlight with this fact is that okay, in classical probability, we have just Finetti theorem. Of course, there's Finetti theorem for, I don't know, discrete probability spaces. There's one for Borel measurable spaces and so on. But they all somehow can be related to each other. But in the categorical sense, we in fact have somehow independent Finetti theorem, which have different assumptions and maybe also different conclusions. But to be honest, I also don't have a good story of what that exactly means. But it's an interesting feature of this. When you go to the abstract level, it's not always so clear that you take one result from classical theory and it corresponds to precisely uniquely to one result in the general theory. Yeah, exactly. So it is a kind of statement of conditional independence, that the outcomes are independent conditionally on some variable w. But here in the assumptions, I don't have this distribution object, and so I cannot identify it as the space of measures over X. So I still get the conditional independence statement, but I don't necessarily get the definitive measure. So it's, in some sense, I have weaker assumptions and weaker statement. Yeah. And the very last thing, which I will just blitz through, is a recent result on the strong law of large numbers. So this has been published this year, where, okay, this is just an intuition for what we are doing, but in the strong law of large numbers, often we are considering the average of some number of trials, and we want to say that this average converges to the mean of the distribution. So that's the strong law of large numbers. But actually, we find out that in the categorical setting, there's a more natural statement that we can express, which is the Glivenko-Cantelli theorem. This is a stronger statement than the strong law of large numbers. And that says that basically the relative frequencies converge to the cumulative distribution function of the original distribution, of the original measure. And so, of course, if you have the relative frequencies converge, then also the average converges. So this is the statement that we want to show. And okay, in order to do that, we have to express these relative frequencies. And so we have this notion of an empirical sampling morphism, which basically takes, it is a morphism that takes an infinite sequence of observations and produces a measure over the original sample space. And the idea is that it expresses the idea of taking limits of relative frequencies of the sequences. And yeah, sure. Yes. Yes. No, we don't get certainty, no. Yeah, it converges almost surely. So this we have to use with probability 1. Yeah, indeed. And so yeah, we have these axioms for what the empirical distribution should satisfy. And then given that, we have the theorem, which again has this almost surely equation where the empirical distribution as a distribution is almost surely the original distribution. And this, if you instantiate it in Borel stock, you get the Glivenko-Cantelli theorem. And if you apply another morphism on top, which is the morphism of taking averages, so you just take a measure and you look at the first moment, then you get the strong law of large numbers. So in this way, you get both somehow quite directly. Okay, there are some other theorems that we have been looking at. There's Aldous-Hoover theorem. There's like a Finetti theorem for arrays or matrices. There's ergodic decomposition. We can prove that idempotent split. And there are some other theorems, 0-1 laws, and so on. They follow a similar pattern. Thank you. Yeah.
Great, thank you. Do we have questions?
Can you recover Okay. Can you recover finite definitive theorems or finite results?
Not yet. So all of these, you have seen we have the infinite products, and the statement is only for the infinite product, so in the limit. And for the finite cases, you would want something like the rate of convergence, or somehow like some bounds on the convergence. And these kind of statements are not accessible in this language because we also, okay, at the moment we cannot do it because we don't have these numerical like bounds or inequalities. There is some notion which I didn't go through, which is this notion of conditional inequality. So you can define, like, in terms of the diagrams and existence of conditionals, you can define an inequality between morphisms that specializes to inequality between probabilities. And so for me, I mean, we haven't thought about this, but this goes in the direction of expressing statements like that, but we don't have it yet.
More questions?
Thank you for the great talk. Why? So in quantum mechanics, we have we can use monotone categories and so on, and we have like a notion of an effect.
Yes.
And it goes from a wire to not a wire. You have it up there in the tanks.
Yeah.
And why don't you use that? What's the problem with using that as conditioning?
There's no problem.
Of a sample or something.
Yeah, so some people have considered this. Of course, then if you have these effects, then they're not normalized. They're unnormalized. And so you have to drop the normalization condition. Then you are working with somehow variation of the structure. And yeah, there are some works also on that. It's you can make some connection between, yeah. Actually, maybe one point on that is that one interesting thing that people have looked at is the difference between different kinds of updating. So there is the notion of Pearl conditioning or Jeffrey conditioning, and you can see it quite nicely with the diagrams, like how they differ. And indeed, there it's nice to look at the effects or the caps. Yeah.
So could one go the other way around and say, suppose I want to argue in the face of uncertainty or reason in the face of uncertainty, then it's kind of, is there a reason why I should take the axioms of a Markov category somehow to describe some of this? In other words, is there kind of an uncertainty interpretation, like fundamentally where these principles come from?
I think not necessarily. The closest somehow justification for the axioms, somehow like intuitive justification, or maybe like, yeah, would be to say that they express properties of classical information and the flow of classical information that we expect. But I don't find it's like such a strong justification, to be honest. Like, it's more like looking at the examples that we want to capture and kind of extracting the features or patterns that they have. Yeah.
Right. Okay. Fair enough. Another thing that I found it really interesting that you have this notion of expressing almost surely in a diagrammatic way.
Yeah.
And the law of large numbers. Now, I mean, conceptually, there's often a problem seen in the law of large numbers when you try to use it to ground the notion of probability in like terms of deterministic notions. Like you say, well, the probability is definitely the frequency that you see in the long run.
Yeah.
Well, it's not just with probability 1. Right?
Yeah.
But could one sort of repair this argument somehow by using this language, or like ground what we actually mean by these objects, which could be probability distributions in terms of how they behave in these sorts of diagrams? I mean, it's a bit vague what I'm asking. I'm not sure if you see what I mean.
Maybe if we go to the law of large numbers, not the average, but the actual distribution. I don't see it from here because I mean, to get the distribution, the almost surely is with respect to the same distribution. So there's some kind of circularity in there. Yeah. I mean, maybe there would be like a stronger version, but I don't see it. And in some sense, like our experience is that, you know, people have been working on the measure-theoretic side of these things for a long time, and it's usually very unlikely that by just going to the categorical version you find something like completely like revolutionary on the classical side. Like,
yes, we expect to find the same sort of self-consistency of the thing, but not the way to ground it in some deterministic notion.
Yeah, I think not. Yeah.
Okay, still it's cool that you can do this. Okay, well, more questions. If not, then let's thank Tomasz again.
Thank you.